Hey Science 8s, it's Manchak here with your last video lesson for Unit D, Mechanical Systems. You made it. We made it through an entire unit through isolation teaching and learning and doing that somehow. And I think that's amazing. If you made it this far, thank you very much for sticking with me through this entire unit. Before I get into talking about Unit D5, or sorry, Concept D5, I'm just going to really quickly run through what we've done so far in the unit, just so you have a recollection of what we did. So we first started out with Concept D1 talking about the six simple machines and evaluating those and figuring out what they are, illustrating how they use input force and to move a load and all of that kind of stuff. Then we looked at complex machines, which are made up of two or more simple machines working together to make something happen, to make a machine operate. We moved into talking about mechanical advantage and speed ratio as a way to describe how good a machine is at making our lives easier, right? Mechanical advantage means it's making the input force less to move the same amount of load. And the greater the mechanical advantage, the more you can move with that input force. Speed ratio was looking at how it translates a little extra effort into making something happen more quickly. We talked in the last concept about work and energy and the relationship between those two, and how doing work on an object means you're putting energy into that object, or transferring energy into that object. And then we talked about hydraulic and pneumatic systems and what they do, and how a hydraulic system is an amazing machine at moving large objects with minimal input force because of pressure in a fluid, particularly liquids. And then today, what we're going to get into is what we're calling evaluating machine and changing mechanical devices. So we're going to take some time to look at how we can look at a machine and decide whether it needs to be improved on, how we could improve on it maybe, and what sort of considerations we might make when designing a new machine or designing an improvement to a new machine. So this is what we're covering in this concept, and in general what it means. So we're first going to talk about what it means to evaluate something, and I'll do that in a moment here, just very briefly. Then we're going to jump into talking about efficiency and effectiveness, versus qualitative versus quantitative, and looking at what that means. We'll talk about function and design in evaluating a machine. We'll talk about environmental considerations. Then we'll take a quick look at a case study related to one kind of machine and how it's evolved as time has gone by, how we've changed it to meet function, design, efficiency, effectiveness, environment, all of those kinds of things. And then we're going to lastly look at how technology develops through change. And I'm going to talk briefly about how science can drive technology, or technology can drive science. The textbook pages you'll cover for this concept are 305 to 320. I have one video resource, and I'll talk about this one right at the very end of the first part of the lesson. I'm going to get you to go back and look at something we looked at the first or the second concept in the unit, and evaluate the machine in that based around what we've done so far. I'm going to have you guys reading something on pages 310 through 312, and I'll talk about that when we get into the notes in a second. You'll have a couple of practice questions out of the textbook, no worksheet on this concept. And then you'll do your practice quiz as usual, wait for feedback, and jump into the exam. So the quiz. So that is where we are at right now for D5. So let's jump in and have a look at how we can evaluate mechanical devices. So this is section 3 of this unit, and it says science, society, and the environment are all important in the development of mechanical devices and other technology. And what we're going to do for the first bit here, this is sections 3.1 and 3.2. I've already gone through these in detail already, but we're going to really just look at what a machine. We'll look at, a machine is meant to make our lives easier. How do machines evolve over time? How do they change because we need a different design, or maybe we've got some better science out there to improve the machine, or whatever it might be. Maybe develop a few ideas of how we could evaluate a machine if we wanted to do it ourselves. And then we'll talk a little bit about how science and technology are linked when it comes to machines. So, evaluating mechanical devices. Mechanical devices have evolved over time because of science and because of the development of new technologies. Okay, and like I said, I'm going to talk about that just a little bit right at the end, I think, and make this connection. But the design and function of a mechanical device is related to its efficiency and its effectiveness. So how, efficiency, we've already looked at that, is how much of the input force is translated to output force. Are we losing a lot of energy in there somewhere along the way? And effectiveness is how good is it at doing its job? Is it we're going to see right at the end of this section, is it like a Rube Goldberg machine where it is this ridiculously complex machine and all they're using it to do is flip a page in a book? That took them 4 hours to set up this ridiculous device that'll take another 4 hours to reset it. How effective is that kind of device? We're also going to look at what effect it has on the environment and how advancements in science through knowledge, trial, and error can also stimulate a change in a mechanical device. So mechanical devices are constantly being evaluated to find ways that they can be improved. And I think we just need to look at some of the devices that we have in our world and that we use frequently in our world to see they have evolved over time. I mean, a computer is a great example of that. How we could have a pocket computer like our phones now, and we can carry that around. That is, this phone is far more powerful than the first desktop computer that I had when I was a kid. The games that I can play on this could not be played anywhere close to on a device 20 years ago or 30 years ago when we first got our first computers in our house. So think about that, is that these machines change as time has gone by. And we're going to go and look at that, some of those examples as we move through this section. So here are some criteria that we can use to evaluate whether a device, a machine, does what it's supposed to do, whether it's something that we want to buy, whether it's something that needs improvement, something along those lines. So when a device is broken down or become ineffective in performing its function, many decisions as to what new device will replace the broken device have to be made, and we need to keep some criteria in mind, because we want to make a machine that is better than the one before and ensure that is what's happening. So the list of criteria that we might use to determine, this is just what I'm suggesting might be useful, is to look at the things of what is the use of the machine? Why do we use it? Okay, if we're making a modification to a device that makes it less usable, is that modification worthwhile? What's the cost of this modification, and is the cost of this modification going to make the machine very expensive and make it not worthwhile for somebody? One of the things that's a big one that plays into a lot of devices is what are the aesthetics of it? What does it look like? I think a great example of this is a minivan. People hate minivans. A lot of people hate them because they perceive them to look ugly, or they have some sort of a stigma attached to them. Yet they are extremely useful machines. They are very practical. They serve the purpose of moving lots of people very, very easily. They are cost effective when it comes to moving people efficiently and effectively. They tend to be relatively good on the environment for what they are. All of those kinds of things, but the aesthetics aren't there. They don't make somebody feel good or appear the way somebody wants it to appear. Another way to evaluate it is workmanship. Is this a device that is going to last for a long period of time, or is it a device that's going to break down after a few uses and then you're going to have to replace it? And a lot of times we link aesthetics, cost, and workmanship together. Often workmanship is strongly associated with great aesthetics. The device looks really good, but it costs more. So if we wanted a cheaper device, often we drop off aesthetics or workmanship, right? Does that kind of make sense? We can play around with that. And remember, workmanship is how well designed and constructed the device is. So lastly is reputation. What is the reputation of the device itself or the organization that's manufacturing the device, and how does that play into its use, purpose, cost, aesthetics, whatever it might be? So when you look at a machine, or you're maybe buying a machine or something along those lines, these might be some of the things that you consider to evaluate that machine, that device. So let's talk a little bit about efficiency and effectiveness. Mechanical devices are designed to work efficiently, which we know can be calculated by dividing mechanical advantage over speed ratio, or we could do output force over input force if we wanted to. And when we do a mathematical calculation and we end up with a number, what we call this is a quantitative measurement of efficiency. So this term quantitative is based around quantity. And if you think of quantity, that means a number of something. So this quantitative measurement is going to have a number or quantity associated with how efficient the device is. We always contrast quantity with quality. Okay, qualitative terms can be used to describe how quickly or easily a device performs the task, and if it's efficient, it does its task well enough to meet your needs. So a qualitative measurement of efficiency might be just saying, hey, yeah, I did that really fast, or yeah, it was really easy for me to do that. That's qualitative. I haven't supplied a number to you, but I've told you how it helped me, right? It made it fast, or it made it easy. Okay. Quantitatively, I might say, yeah, well, it appeared to have a mechanical advantage of 4 or a speed ratio of 6, right? Those are throwing numbers at the situation rather than throwing qualities at the situation. Qualities meaning quickly or easily or something along those lines. Efficiency and effectiveness can be compared when analyzing the designs of different devices that do the same task. For example, looking at a bicycle. Okay, a mountain bike is a much more efficient and effective machine to use when you're riding in an off-road situation than a street bike might be, or than a tricycle might be. And so these are the ways that we might evaluate this. So usually what we're doing is we're looking for the best combination of efficiency and effectiveness at a cost that you can afford to do whatever specific task you're trying to do. And maybe if you're buying a bike, and you might do some off-road biking, but maybe you want to do some biking on the street, maybe there's a hybrid of the two that you buy that allows you to do a little bit of each and still have it cost effective and meet your needs. Okay, so when we talk about efficiency and effectiveness, we're talking about how well does it meet your needs, and how does that relate to cost efficiency and usability and all of those other kinds of things. Next thing we'll talk about is function and design. So scientists, engineers, inventors want to develop mechanical devices that work best for their work they're designed to do. So the function of a device is the purpose, and the design is the form. So basically what we're doing is function is what is it supposed to do, and design is how is it going to look? What is it going to look like? But we always want to make sure that design suits the function, meaning that if your design is overly elaborate and big and monstrous, and it looks really cool, but then you can't do what you're supposed to do with the device, then design and function aren't working together properly. We need function and design to work together properly for a machine to be effective. So lastly, evaluation for development. Another reason for evaluating a device might be to determine how it can be improved. We've talked about this briefly. So the environment can have an impact on the design of the device as well. Maybe a device that was designed in one part of the world may not work as well somewhere in another part of the world, right? That's that example here of a mountain bike versus a road bike, right? The development of mountain terrain bicycles came as a result of how the bicycle would best function in rough terrain it would be used in, right? So we wanted people who wanted to ride in off-road situations, off-road in trails that have logs and rocks and all these other kinds of things. They needed a bike that could handle that. And so the development of the new bike came from evaluating the reason why somebody might be riding the bike. We also need to consider the environment in what's going on, and consider it in how we design something or how we evaluate it. And a negative impact on the environment should not outweigh the usefulness or effectiveness of the device as well. So we need to consider what impacts the device is going to have on the environment. We should not be designing something you know, that is this amazing machine that does stuff, it is going to, if it's going to completely destroy the environment as a result of what we're doing. So that needs to be a consideration as well. So we need to look at efficiency and effectiveness. We need to look at function and design. We need to look at impacts on the environment. We need to look at things like usability. All of those things are important when evaluating a device. So what we're going to do now is we're going to take a little stroll through and evaluate a mechanical device that is very, very, very simple. And it's a pop can opener. So most of you are familiar right now with a pop can, I hope, where you have a pop can and you pull the little tab on the top and it opens the pop can and then you can consume your beverage. That is the 2020 version of a pop can opener. But over the years, that device has changed. And we've evaluated and reevaluated that device as time has gone by to decide whether it is still effective or to change it to make it more effective. So improvements can be made, can make the device more convenient and can affect people using it as well as the environment. So all of these things need to be considered. The history of this device shows how trial and error can play a role in improving technology. The pop can opener went through four distinct designs. Okay, and by the way, this is based off of page 310 through 312 of your textbook. So if you wanted to go have a look at that when we're done at this, it might fill in some of the blanks here. But pop can opener went through four distinct designs: church key, a removable tab, buttons, and then a non-removable tab. And each new design was the result of improving upon the previous design, which we discovered after evaluation had some sort of a flaw associated with it. So it's changed over the years, and these changes help to explain how evaluation can lead to improvement. Okay, improvement. I think we've already talked about all of this. So we're going to move on to the next one. I think I jumped ahead instead of ahead. See, I'm smart. I'm getting good at this online teaching thing, guys. I don't know how many of you even watch these videos anymore, so I might just be being goofy for the heck of it and just trying to entertain. Anyway, let's jump back into this. Pop can opener, basically the evolution of the device. To pour a liquid out of any container, you need two holes or one large hole. Okay, with two holes, the first hole allows air into the can, and the second hole lets liquid flow out. If you only had one really tiny hole, it really doesn't allow anything to get out in any regular rate. It'll come out. It's just going to take a lot of time. And so popping a second hole in a can would allow air to come in and the liquid to come out the other one, and then it would come out much more quickly. So here's the evolution of what's going on here, and I'm going to move myself up in a second here so you guys can see what's going on. So the first can opener design was in the around 1810, and basically it was an iron can. It kept things sealed and had to be opened with a hammer and a chisel, which does not seem terribly practical to me. So then we get a steel can later on. Okay, steel cans are, iron's pretty heavy. Steel can would be a little bit lighter, and it would be opened with something called a church key. You may see one of these things in your house, right? One side you could open like a bottle with, the other side it's got this pointed, simple lever going on here, which would put force onto the top of that steel can and allow you to open it. The problem with this is you always had to have a church key handy to get that steel can open. And if you didn't have one, you're not opening that steel can. In the mid-1900s, aluminum cans came along. Aluminum cans were great because they're lightweight. The can opened by wrapping the metal around a key called a side seamer. And really what you would do is you would just roll it. And you can kind of see that over here. This is this little key called the side seamer. And then what you would do is you basically break the seal and then just roll it up to open whatever's inside. Old sardine cans, I remember, used to have something like that. So it was great because it was lightweight, but the problem is it created a lot of sharp edges, which could be a problem for cutting those kinds of things. In 1963, the aluminum can got what's called a removable pull tab. Basically, it's a ring tab that made it easy to open, and so all you would do is hook your finger into it, pull it off, and throw the ring away. Okay. Couple of problems. Sometimes the ring's detached from the tab and you couldn't be open. You pull it and nothing would happen. Or you have that little ring that you use to pop open the cap. Well, it becomes a litter problem. People don't find a garbage can. They're lazy. They toss it on the ground. We have them all over the place. They become a safety hazard because of the sharp edges where you peeled it off. So then we end up with push button tabs in the mid 1970s, which solved the problem. But they found that it was hard to push the button to get open, and consumers didn't like using cans with two buttons. Didn't like using. That's an aesthetic problem. People didn't like it. It wasn't that there was an inherent problem with it. It's just people didn't like it. They didn't enjoy using it that way. So finally, we end up to fast forward to around 1980, where we're at today with this design is a non-removable pull tab. So what they called the ecology top, because the tab stayed attached to the can. We know that. We grab our can of pop, pop it open, fold the tab back, drink away. We could break it off if we wanted to, if it was annoying you or whatever reason. The ring would not. The only disadvantage is that maybe the tab wouldn't puncture properly, or it would break off. But it was the best solution we have to date so far, and I don't think we've made much modification. Anyway, that was me talking a lot. What I want you guys to do is maybe hit pause here for a second and just go back through this. And what I want you to do is look at how this evolved, what these changes were that took place to make this happen. There was a problem with the previous design, and the next design tried to solve it. And then we found issues with that design, and the next design tried to solve it. And I wonder where we're going to get to next. I mean, we're in 2020 now, so we're about 40 years later of this non-removable pull tab. Hey, what's the next evolution of the pop can puller? I don't know. Okay, so hope you gave that a little bit of thought. Now, what I want to do, the changes to the pop can didn't happen by accident. Okay, this is what I just talked about. Careful evaluation, improved designs to perform the function helped make the can opening changes more efficient and effective. Questions about safety, convenience, environmental effect, recycling potential were all factors or criteria that contributed to the improvements being made. Basically, they ask themselves, what are you looking for in the device? It's one of the first questions you should answer when evaluating the device. Is aesthetics on the top? Is workmanship on the top? Does it have to be cheap because you don't have a lot of money, or you're cheap, kind of like I am, right? What does it do? So I thought this might be a good opportunity for you guys to hit pause and watch the Rube Goldberg thing by OK Go again, and look at that machine and what the purpose of the machine is. You might have to wait to the end to see it, and ask yourself, is this a machine that would be something that anybody would do? And the whole idea behind a Rube Goldberg machine is that it's not. It's meant to be a whole lot of fun, and that's about it. And I've been seeing tons of stuff with Rube Goldberg machines all over social media since the pandemic started, because people have a lot of extra time on their hands and they're going out and they're making these complicated things in their house. All to basically, maybe shoot a pool ball into the corner pocket, or to, open a door, or whatever it is. Those machines are not designed to be effective or efficient, but they are designed to be aesthetically a whole lot of fun. Anyway, go ahead and have a look at that video if you'd like to. Where we're going to jump to now then is, and there's some practice questions I want you guys to do. The last bit of this unit we're going to jump to is talking a little bit about technology and how it develops through change. So new materials and technology, human and environmental needs all contribute to the development of changes to current devices. When a failure occurs, modifications must also be made to ensure the device performs its intended function effectively and efficiently. Trial and error also play a role in technology development. Early devices were usually operated by hand. Improvements to the device by making it perform its task more easily came as people tried to make the device perform more efficiently with less effort. And then invention of electricity also contributed to improvements. Okay. Now, here's where I wanted to take just a moment and talk about science and technology and how they play off of each other. And I talk about this a lot in other courses as well. So you may hear this come up again next year in grade 9 or in grade 10 or beyond. Science and technology work together quite often, but it doesn't always work in the same direction, right? We don't always come up with the science first. We don't always come up with, hey, we know how this is going to work, so we can build something from this, right? Because we've gone and done the science and we figured out how something works. Sometimes it works that way. Sometimes we get electricity, we figure out how it works, and then we can invent technology that comes from that. Other times, somebody built something, doesn't know how it works, but it works, and then science has to take it and break it down and look at it and figure out how it works. So sometimes science feeds technology, right? We learn how electricity works. That feeds us, Tesla and alternating current feeds us into using alternating current in our homes because it's way easier to work with. Or technology feeds science. So somebody goes and invents something, and it could be something as simple as you look at an item in your gardening tools and go, that doesn't work well. I wonder if I made this modification, if it worked better. Oh, it works better. Hey, great, I'm going to use this. I'll make some for my friends, blah, 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 blah. And then a scientist gets their hands on it. Well, why does this work better? Then they go and they explore, they experiment, and they figure out why it works better. So sometimes science drives technology, sometimes technology drives science. It doesn't matter, it still advances the technology. So here's some examples. Advances in science result in new technology. Charles Coulomb first identified electric charges in the 1700s, but it took almost 100 years to make electricity widely available to major Canadian cities. And it took until the 1940s to make it available to most communities in Canada. As scientists and engineers learned more about this new energy source, they found ways to use it, use new technologies such as light bulbs and the electron microscope. So sometimes technology drove science, sometimes science drove technology. New technology can also develop from unrelated research. For example, maglev, which is magnetic levitation trains in Japan, operate on superconductive magnets powered by electricity. They can travel at speeds over 350 kilometers an hour, basically floating on the rails. They don't actually touch the rails, they're actually floating on it through magnetic repulsion and all of this stuff. The technology for maglev resulted from physics experiments using particle accelerators, which are huge machines that are used to break apart atoms and other particles to try to figure out what's inside them on a small level. But from what they were doing with these particle accelerators came the idea, well, I wonder if we can use magnetic fields to lift something big like a train up and propel it forward. And so they were able to create powerful magnetic and electric fields which interact, which cause trains to fire forward at super fast speeds. Really cool stuff. Science driving technology. New technology can also result from changes to human society. So science can drive technology, but society can drive technology as well. Robots were originally popularized in movies and comic books, and the word robot actually comes from the Czech word robotnik, which means workers or slaves. They were thought to be human-like machines that could do the work of humans. The term was originally used in a play where millions were manufactured to work as slaves in factories. Most robots today don't really appear to be human-like, but they do the work of many humans, mostly in industry. So we know that robots are used to help us out with a lot of things that are really challenging for us to do or dangerous for us to do. So they weld car bodies together, they can defuse bombs. The most advanced robots can be controlled by humans but are much steadier than humans, and so they can do surgery, they can help the handicapped, they can even explore other planets like the Mars rover did. So society dictates when we might need a new technology. And then lastly, the environment can dictate what needs to happen with new technology. Since the early 1960s, a lot of people attribute it to Rachel Carson and the book called Silent Spring. The environment has impacted technological development because people wanted to repair the bad things we were doing to the environment. So we've developed new technologies to help prevent the damage. So for one thing, we've decided that we can take used plastic and we can recycle it, or paper and we can recycle it. That's a new technology. Instead of going down and cutting more trees or making more plastic, we can just recycle it. Processing materials over and over, making them biodegradable, would address some of these issues as well. Other technologies like oil skimmers could help clean up the environment more effectively. We developed new technologies to make our planet cleaner as well, like more fuel efficient engines in vehicles or electric motors in vehicles that allow those vehicles to work as well. And that's all being done not only because they're efficient and they save us money, so it's an economic factor, but it's also an environmental factor because they burn less fuel. All right, so that is it, ladies and gentlemen. That is the end of concept D5 and the end of our unit on mechanical systems. That has been it's been amazing to try to teach you guys to teach you through remotely this unit. I've learned a lot. I hope you guys have learned a bunch about mechanical systems and how they work. As always, please do your practice questions. No worksheet on this concept, no activity. It was just a really quick, how do we evaluate mechanical devices? So make sure you go over your notes once or twice more, do the practice questions, and then jump on and do the practice quiz. Please make sure you wait for feedback and then move on to the summative quiz when I've given you the okay. This means then that next week we are jumping into Unit E, which is saltwater and aquatic ecosystems, and something that I'm excited to teach you guys, especially because the weather's started to get really nice outside, and that's why I leave it to the end of the year. So I hope you've found this unit interesting. As always, if you need any help with anything, track me down via email, pop into my office hour each day and let me know how things are going, or just pop in to say hi. Hope you guys are staying safe and healthy, and we'll talk soon.